Hello and welcome back to another video with It's Dr. Dan, and today we're going to be learning about enthalpy and stoichiometry. Now, when it comes to chemical reactions, what is one of the most important concepts is that when a reaction is happening, bonds are being broken and new bonds are being formed. And depending on your course, you will have to do different types of calculations, maybe using thermochemistry tables, maybe just using stoichiometry in order to calculate different values of heat or mass or moles. Now, why is this so important? Is once again is that all chemical reactions they absorb or release heat because energy is transferred within a chemical reaction, right? If you think of the sun shining above, it is transferring heat to all kinds of different plants and things around, right? So if you think of plants, photosynthesis is occurring because it's absorbing that UV light, which is energy to help those reactions happen. Heat is always transferred. Whether something feels cold or whether something feels hot, you are able to actually calculate the number of joules or energy that's being released. So this video specifically will look at the stoichiometry, meaning that we have to understand how to use a balanced chemical reaction to be able to actually determine the stoichiometry. We will be calculating the masses, meaning that we're going to be using molar mass as a component, and we're going to be using the mole to mole ratios that come with the terminology found within the heat of or within our enthalpy of our reaction here. So we're going to be focusing on delta H, how to calculate that, and let's take a look at some of the different calculations and what this involves. The first thing that we have to make sure we understand as well is knowing our key vocabulary and terms, right? You don't want to go into your first exam or your homework, see all these new terms that you just don't recognize, right? You need to be able to understand what do they represent. The first thing is understanding the different types of heat reactions, which is exothermic and endothermic. Exothermic is all about when we're referring to how much heat is being released or energy is released, meaning it's coming out, right? It's being produced as a result. It feels really hot when we have something as exothermic, meaning that when we look at, let's say, a chemical reaction, we'll see that, okay, A is going to B, right? Reactants to products, and it's generating heat as a product. So that's really important to realize. Heat is a product when it comes to exothermic. So you might also have to look at energy diagrams like the one shown here, where if I have, let's say, two reactants, so I have hydrogen and chlorine gas, they're combining together. And as a result, when that happens, they're going to make HCl. Now, in order for this reaction to happen, you can see that heat is a product, right? So it's going to release 185 kilojoules. So the way that we can represent that is using energy curves like the one shown here, where essentially if I have my reactants, the reaction's going to start, and then all of a sudden it's going to release a ton of energy when the products are formed. And that's the key thing is, right, there's energy required, it's being released. So when you see that there's less energy in the products, that means that you release. And this is favorable, right? So this is spontaneous when this happens. Exothermic is favorable. So the way that we show the delta H of the reaction is we're simply just reading what's in this formula. Now, being that we have 185 in the products, being it's exothermic, we're going to represent that using a negative value for exo. So exo is negative. So when we write this and say, hey, delta H, we're going to put negative 185 kilojoules is going to be our answer here for how to represent that. And that's going to be 185 kilojoules per mole. All right. So that's going to be our units. And we're going to tell you how many moles that is what's all going to be. And as you can see too, heat is a product, which is very important. Let's look at endothermic. Absorbing heat. Heat is required to make this happen. So being that heat is required here for the reaction to occur, we need to absorb it or it's not going to happen, right? So in order for like photosynthesis to occur, for plants to produce oxygen, they need to absorb sunlight for that to happen. So that's an example of endothermic because it needs to absorb energy. Now, when we're looking at these and trying to understand, all right, how can we represent it? Well, generally the reactants by themselves, they are happy. they actually don't have the urge to react when it's an endothermic process. There needs to be something to kind of kick it off in order for it to occur. So if you give it energy, let's say if you have nitrogen, oxygen gas, let's say in the upper atmosphere, and it's absorbing UV rays from the sun, and they combine together at the right time, well, then you can actually have it where they can form nitrogen monoxide as a product, which is a very global warming gas or a dangerous gas, meaning that energy had to be absorbed for that to happen. It doesn't occur by itself, it's not spontaneous. It needs energy to happen. All right. So when we have that, you can see that the energy is written as a reactant here, right? It's plus 180 kilojoules in the reactants, meaning that we are going to write this as a positive this time. And it's going to be 180 kilojoules per mole is going to be our reactant. Okay, so that's step one. What else can we get from looking at these different values? Next part is how to use reaction enthalpy as a conversion factor, which is generally the most important part of using this in stoichiometry. Stoichiometry is just word problems and dimensional analysis wrapped up in chemical reactions. So when we're using this, it's all about the amount of thermal energy that's absorbed or released by a chemical reaction. And this be specific, this is at a constant pressure. So if you're trying to use this in terms of maybe more general chemistry 2 type calculations, you're going to need a different formula to calculate these. You can still use these, but it might be a different process for your course. So keep that in mind. Now, when we are using these are conversion factors. So what you need to do is be able to read a chemical formula. It might look like the one here. So this is a combustion reaction where we have propane reacting with oxygen gas. So propane is C3H8, and it's going to burn and make CO2 and water. Now, as you can see above, I have the delta H of the reaction listed, and it says that it's negative 2044 kilojoules. So what can you learn from that? Well, the first thing is that, okay, well, that's exothermic because it is a negative symbol that's here. The next thing is that technically the heat could be written as a product as well. So there could be two different ways that this can be illustrated. So let's say if I if I make the chemical formula a little smaller, this could also be illustrated in the actual chemical reaction as a product as well. So we could say plus 2044 kilojoules written inside. So there's two different ways that the same information can be shown, which is really important that you're paying attention to signs and how it's being shown. If energy is being given to you in the problem, 99% of the time it's probably an enthalpy problem. All right. Now, what else can you get? Well, being that we know that this is negative 2044 kilojoules, this is for every mole. All right. So if you remember from before, it was negative 2044 kilojoules, and this was over moles. But what number of moles? How can you relate it to? Well, it's all related to the chemical equation that's above. We can actually relate it to the number for all the different coefficients that are in the problem. So for example, we can relate that to any of these. So if I say negative 2044 kilojoules is released for every 1 mole of C3H8 that is burned. Okay, now where did I get the 1 mole? Well, that's because essentially we have a 1 that's in front of C3H8. So we can use that. Another example is, let's say if I use the 5O2. Well, if I have 5 moles of O2, that's also equivalent to negative 2044 kilojoules of energy released, because this is a complete balanced chemical equation. That's the important thing. It has to be balanced. So we could also do this with the products too. We could say, hey, I have 3 moles of CO2, and that's going to be also equivalent to, hey, you might have guessed it, negative 2044 kilojoules for this reaction. Keep that in mind, this reaction. Every reaction is going to have a slightly different energy value. And the last one is, well, if I have 4 moles of water, I can also relate that to 4 moles of H2O all over, once again, you might have guessed it, negative 2044 kilojoules per 4 moles of water. So all of these terms, all 4 of them, are available to you. Now, which one do you use? It depends on the problem that's being presented to you. So if you're being given, let's say, the mass of propane, you would use the first term over here. If you were given, let's say, maybe the mass or moles of oxygen, you would use the middle one, and so forth. You have to read the problem carefully, which we're going to show in our next example. All right, so let's look at the tips and tricks of how to solve these word problems. How much heat is involved with the combustion of 1.18 times 10 to the 4 grams of propane? And we have the same balanced chemical equation that we had in the previous example. So what exactly do we need to do here? Well, being that we got to first highlight what information we were given in our problem, and we can see that, hey, we were given the exact mass of propane that was used in this reaction. So we had propane, we are going to burn it. Now, the thing that is being asked of us, or what is our desired, is that we want to know how much heat there is. So how exactly can we do it? And we were also given what the delta H is as well. So we have a couple different key values that are very important here, which we can try to use to figure out what the different pieces of information are. So in this problem, what we need to do is kind of map it out for ourselves. We want to start with our grams, right? So as always, you want to write out all the little pieces of information you're given, which first thing is your desired or is your given terms, right? So we have 1.18 times 10 to the 4 grams, which is a term that's by itself, right? You always want to start with a term that's not a fraction because it's easier to start with. We're going to write out our t table, which what all a t table is the equivalent of fractions multiplying by each other. So top and bottom is your fraction. So what we need to first do is we need to cancel out grams and get it to moles, because what we need to use is our enthalpy value, right? Which was kilojoules per mole, right? We can relate that to our chemical equation. So being that this first part is grams and it's grams of propane, so we should label that. What we are going to do is essentially cancel this out with our molar mass of propane. So using molar mass to do that, what we need to do is essentially calculate and look up all of our values from our periodic table. So being that I have carbon and hydrogen conveniently over here, we are going to take 3 carbons, add that to 8 hydrogens, add it all together, and we will get 44.097 grams per mole for our molar mass. Now, when we use that, we're going to plug that in and cancel our units. So grams is on bottom. Notice how they're opposite of one another, just like we've done in the past. And this is always equivalent to 1 mole of C3H8. Now, being that our goal is always the mole, we got it there, which is fantastic. What we're going to now do is we need to convert from moles to energy, right? Because we want to know how much heat, what is the number of kilojoules that's desired. And what you need to now do is the equation has to be balanced for you to be able to do the step we showed earlier, right? Which we have up above. We have the balanced chemical equation all the way up top here. So what we can now relate to is being that we started with propane, and what we can see is that there's 1 mole of C3H8 from our balanced chemical formula. And what is that equivalent to? It's at negative 2044 kilojoules, right? So just like so. Now, what we're going to now see is that our units cancel, which is great. And we have it in kilojoules of C3H8 for the energy of that. And what we are going to do is we take 1.18 times 10 to the 4, times that by 1, times that by negative 2044. And we're going to divide it by 44.097, and then divide that answer by 1, and you will get your final answer. So when you put this in your calculator, what you should be getting is 546,958 kilojoules. Okay, so it's a very, very large number. Typically with these, we always want to round them to sig figs and put them in scientific notation. So we can see that, hey, we're going to be moving this decimal 5 times. And we want to round it to 3 sig figs because we started with 3 sig figs at the very, very beginning. So what are we going to have in the end is negative or sorry, negative 5.47 times 10 to the fifth kilojoules is your final answer for this problem. Okay. So this is how you can find the amount of energy. Now our last example is going to be find how the amount of mass that was either created or used to make this amount of energy. So we're going to do the backwards. Let's take a look at our last problem. Let's practice this problem. So what we have is diboron trioxide, which is a solid formed by the reaction of igniting boron powder in oxygen gas. And what it's telling you is that we also have a delta H reaction of negative 1273 kilojoules. Now, and it's asking how much diboron trioxide did you start with if 1690 kilojoules is released? Assume a diboron trioxide molar mass of 69.62 grams per mole. Okay, so these types of problems are very, very difficult because we weren't given the actual chemical equation. We have to read this very, very carefully when doing it. So the first thing that we are going to do is that we are going to balance our chemical equation. Now, what it says is that diboron trioxide. So di is 2, so it's going to be B2. Trioxide is 3, so B2O3, and it's a solid. And it says it's formed. Okay, so formed means that it was created or that it is a product in this case. So we're going to write down the right hand side of the arrow in this case. Now it says we're going to ignite boron powder with oxygen gas. Boron is a solid, so that just is, and B, it's a powder, so that's going to be by itself. Oxygen is a diatomic gas, so we have that as well. Now, when we are balancing this, we have to make sure that we are using our coefficients. So the first tip and trick I always say is let's even the odds. You can see that we have 3 oxygens on the right, meaning it's odd. So let's even it. So we're going to add a 2 in front of that to make a 6, which is an even number. I'll add a 3 in front of the oxygen on the left-hand side. We evened the odds in this case. And now what we can do is balance our borons, and we see that we have 4 and 4 on the left and right. Now, our next part of information that was given to you was the delta H of the reaction, which, as we can kind of see if we pull this out, was negative 1273 kilojoules, which means that it's a product. So we can also relate that to exactly being that it's talking about diboron trioxide, we can relate it to that value as well. We can relate it to the number of moles that is in the problem, being that it asked, okay, if we have diboron trioxide, how much is there? And we release this much energy. So what we are going to do is we're going to define our conversion term just like we did before. And being that we have negative 1273 kilojoules, that's for every mole. And well, which mole we're going to use? Well, the problem asks for B2O3. So this is going to be equivalent to for every 2 moles of B2O3. And you can write this conversion term for all the other values too, but they're not important for this problem. So when it comes to solving it, we were given another value as well, which was that you had negative 1690 kilojoules of energy that was released. So, which is a given term, right? You want to start with that because it's by itself, it's not a fraction. Versus the other value that we have, which is 2 moles of B2O3 is equivalent to that 1273 kilojoules. This term can be flipped one way or another. So you don't know which one to start with. If you choose wrongly, your units are going to be flipped and it could lead to confusion when you're at the end. But the value that's on the left-hand side over here, that can only, you can't flip it, right? It's easy the way it is. We can just start with that. So we're going to start there and we need to use the balanced chemical equation. So what we're going to do is essentially cancel our units. So we'll start with negative 1270. And now we need to cancel out kilojoules. So how can we exactly do that? Well, we need to have kilojoules on the bottom. So what we can use is this term on the top right here and kind of plug this value in like so. And now what we can see is, hey, your kilojoules canceled. Fantastic. That is what we want when we're looking at these problems. Now we have our units in moles. So how can we get grams? Is we need to use the molar mass of B2O3, which was given in the problem. So earlier that said it was 69.62 grams per mole. So let's kind of write that up here so we can write it in correctly. So we had 69.62 grams, and that's equivalent for every 1 mole of B2O3. And now we can see once again, our units are doing what they're supposed to do, which is cancel. And now we're left only with grams of B2O3, which is what we want. So when we are solving this, we're going to multiply everything on top and then divide by what's on the bottom. So we'll take negative 1,690 times that by 2, times that by 69.62, and then divide by negative 1273. And what we are going to get, you'll get 184.85 grams of B2O3, but we need to round it to the correct number of sig figs. We have 4 in this case. It's always being based off what was given in the problem. So as you can see, the number we started with over here on the left is 4. So we'll round this slightly to 184.9 grams of B2O3. And that's how you solve. These are the two types of problems you can see with enthalpy. It doesn't get any crazier than that. Now, the biggest thing you need to make sure you do is you need to be able to predict and balance problems. If you need help with that, refer back to my old videos on how to do that as well. Okay. Thank you so much for listening. I hope that this video helped you. Please let me know if you need any help. Comment below if you do. And feel free to, if this is your first time here, hit that like and subscribe button. Please keep helping the chemistry channel grow so that way it can help more students just like you. Thank you so much, and I'll see you all later. Bye now.